I spend a lot of time on chemistry in my day. I'm like, ugh.
Yeah, I spend a lot of time on chemistry too. Only thing, I keep saying it over and over. I feel like a broken record at the end of the day.
That's how I feel in my group.
That's it.
Okay. So today we're going to be talking, and we're going to start on yield. And the reason why we started on yield, even though I talked about that last time with the other class, but I didn't get a chance to talk about it with you. And I want you guys to get the gist of it. Okay, so when we talk about yield, we're talking about what is actually being produced. So we have the actual yield, and when we have the ideal yield or the theoretical yield. I like using theoretical because it sounds fancy. So ideal will work as well too. Okay, actual yield is what you actually have, what you made, you know, and typically your actual yield is usually lower than your ideal yield, unless you've done something really crazy, which always happens. So in my case, you know, you end up with a little extra, right? And I did tell you guys a story, what happened to me when I was going to quit science and all that stuff, I believe. Okay. So this is one of the reasons why, right? This whole concept, because I didn't understand this concept because I had never, you know, nobody in my family was ever scientists. I was the first person to go to college, you know, and so, you know, but I thought I was the shit, you know, and so when I found out that, hey, you can't be perfect, you know, there's reasons why. Some of the reasons why are things that you do. Some of them are side reactions. Some of them are impurities, you know, and we also have to try to take that into consideration, right? As a good scientist, we try to account for things. Is that correct?
Yeah.
Yes.
Good.
As a good scientist.
Okay, so yield, percent yield is always going to be the actual over ideal or actual over theoretical times 100%. Okay. In most cases, like I said, it's going to be your percent yield is going to be lower than 100%. If it's 100% or greater, you're probably smoking a little bit of crack, or, you know, somebody put something in your stuff, you know, but then you may want to retest it after that if that ever happens, right? But it can happen. Okay. So a solution containing 3.18 grams of barium chloride is added to a second solution containing excess sodium sulfate. Barium sulfate precipitates. Calculate the yield of barium sulfate. If the actual yield is 3.37 grams, calculate the percent yield. Okay, so what would be the first thing that we want to do with this question? We got it on an exam.
You can write out the compound.
Write out the compound?
The chemical equation.
I'm going to write out the chemical equation because we know that this is a reaction, right? So we want to write everything out. Okay, so let's go ahead and start with that. Okay, so what do we have? What are our two reactants?
It's barium chloride and sodium sulfate.
Okay. Okay, barium chloride. What does barium chloride look like? What is the compound of barium chloride?
Would it be
Chemical formula?
Would it be BaCl2?
BaCl2.
Yes. And then
Okay. Is that solid, liquid, gas, or aqueous?
Aqueous? I feel like we did do this.
Heather, you go to every lecture, so you're kind of a little bit of a bias there.
That's very true. I don't know where I'm at anymore. Okay, good point.
Okay, so, and you said the other one was sodium sulfate. So what is the chemical formula for sodium sulfate?
would it be Na SO4.
Okay,
Would it
and
be
then what is that going to
NaCl?
make? Oh, what is it? What is the state?
Aqueous.
Aqueous. Good job. And what is it going to make?
NaCl.
Solid, liquid, gas, or aqueous?
Aqueous.
And it's also going to make what?
SO4. Barium sulfate.
Solid, liquid, gas, or aqueous?
Aqueous.
Did you say aqueous? Are you sure?
Mm,
What does that word precipitate mean?
liquid. Liquid.
Does it mean in liquid?
Gas.
Does it mean gas?
No, I said
Precipitate. Water,
Precipitate.
liquid, dew.
Nope.
Oh,
Don't think
solid,
what was that?
solid,
It actually means solid. Anytime that you see precipitate in chemistry, it means that you're making a solid. The reason why they say precipitate, because it precipitates out. It drops down to the bottom. It forms a solid, drops down to the bottom.
Okay.
So then it's a solid. Okay. Okay, so this is our chemical equation. Can you guys see it up there?
Yes.
Yeah.
Is it balanced?
No, it's not.
No.
Okay. Oops. Okay, what do we need to do to balance it?
Need add it to in front of and the product side in front of NaCl.
Okay, is it balanced now?
It is.
Yeah.
Yes, it is. Okay, so now we have a balanced equation. Okay, so the next thing that we're always going to want to do is start off with our given, right? So we know that this given here is the actual yield. So we know what that is already. We know that that's the yield that we actually got. So we're going to save this one for later. Talk about that one right there. Now, the other one, the other given is, this is what we're starting out with, right? Now we know that a chemical reaction is kind of like a recipe, right? It kind of lets us know how much of everything that we can make, right? If you have so much stuff. So if I have 3.18 grams of barium chloride, I can calculate how much of barium sulfate I can actually make in theory, right? Using my chemical equation. But first, I want to start off with my given.
2.18 grams of barium chloride.
So we have 3.18 grams of barium chloride. Okay, so the chemical equation, like I said, is like a recipe, but it's based upon quantity. It's not based upon mass. Now, when we talk about quantity, we're talking about moles. So we want things in moles. So if I have something in grams and I want to convert it to moles, what is it that I need to do?
You need the molar mass of barium chloride.
I'm going to need the molar mass of barium chloride. So I know that barium, how much does barium weigh? And where would I find this at?
On the periodic table,
On the periodic table. Okay, so barium weighs how much?
137.33.
137.33. Okay, and we have how many chlorines?
2.
So we have 2 chlorines. How much does each chlorine weigh?
35.45.
35.45. So that's going to be what, 70.9? So we add these two together.
That's 208.23.
Okay, we know those units are grams per moles because we know molar mass, molar, moles, mass, grams. So we know it's grams per mole. Okay, so if I want to get rid of grams and I want to convert to moles, how am I gonna manipulate this guy? That 209.23.
It has
I mean,
to be
208.23.
on the bottom.
Okay.
So, and then on the top, 1 mole.
So I'll put 1 mole on top. And that's of barium chloride. And I'll put 208 at the bottom.
Grams
And that's
of barium
grams
chloride. Yeah.
of barium chloride. Okay, and what are we looking for?
For barium sulfate.
We're looking for barium sulfate. So if I look at my chemical equation lets me know the mole to mole ratio, right? So for every 1 mole of barium chloride, I have 1 mole of barium sulfate.
Yeah.
Isn't that what my chemical equation tells me?
Yes.
Okay, so that means that we have 1 mole
Of barium chloride on the bottom.
barium chloride,
And then on top, 1 mole of barium sulfate.
1 mole of barium sulfate. Okay, so if I want to get grams of barium sulfate, how would I do that? So how would I convert from moles to grams?
You need to find the molar mass of barium sulfate.
So I need to find the molar mass of barium sulfate. So we know that barium, we have 1 barium, we have 1 sulfate, 1 sulfur, and 4 oxygens. So barium weighs, we know, 137.33. You guys told me that already. Sulfur, how much does sulfur weigh?
32.06.
32.06. And how much does oxygen weigh?
Oxygen.
It's 50.
Somebody say 16? Like my age?
Yep.
Okay. 16 times 4.
64.
So we have plus that 32 and plus that 137.33. We add together.
That would be 233.39.
You said 233?
Yes.
Okay. So then we have 1 mole of barium sulfate at the bottom.
Yeah.
And then our 233.
Grams.
39 grams
Barium sulfate.
of barium sulfate at the top. So if we go through, look at our units. So we got rid of grams. We've got rid of moles. Barium chloride. We got rid of moles of barium sulfate. And so we're left with just grams of barium sulfate. What did you guys get?
So when it says
Everyone.
ideal yield, are we
Right.
always going to be getting grams?
It can, you can leave ideal yield in moles, or it can be in grams. Both will actually work.
It just depends on the given then, right?
That's right.
Okay.
3.56?
You said 3.56. Oops.
Yeah,
And that's
Grams.
grams,
grams.
barium sulfate. Okay, so now we calculated the ideal yield, right? So then we know that percent yield is what again?
Actual over theoretical.
And so 100?
Times 100.
Times 100, yeah.
So actual over quote ideal or theoretical times 100. Okay, so our actual is
3.37 grams. Over 3.56.
times 100.
Is 94.66.
3 sig figs.
94.7.
Percent?
Yeah, yield.
Okay. Oops. Okay, piece of cake.
That was so fun. I want to do it again.
Excellent. That's what I want to hear. Okay, everybody got it down, right?
Just give me 1 second.
Okay.
Almost got it.
1 second's up. All right, go ahead, Dr. Henry.
Heather, you're supposed to be making friends, not enemies.
Oh.
All right, yeah, you're good.
Talk about that. Okay.
Friend Heather.
I know. I need a friend. Preferably one with 100% in the class.
Okay. So here, the question reads, solid sodium nitrate decomposes to solid sodium nitrate and oxygen gas upon heating. One set of the reaction condition gives 95% yield. What mass of sodium nitrate will be produced by the decomposition of 1.50 grams of sodium nitrate?
Or phone a friend.
Okay, so what are we going to want to do with this?
Find the chemical equation.
Yes, sodium nitrate.
Okay, so we said we have solid sodium nitrate. What does that look like? What is the chemical formula for solid sodium nitrate?
Could it be Na?
I heard somebody say NaNO3.
Yeah.
And oxygen gas.
Is that a solid, liquid, or gas?
Solid.
Okay, and it says decomposes to solid sodium nitrate sodium nitrite and oxygen gas.
Yeah, sodium nitrate.
So what does that mean?
Yields NaNO2 and O2.
Okay. Is that solid, liquid, or gas?
Solid.
Solid.
Right. Solid, right? Okay.
And
And
O2.
we're making oxygen gas,
O2.
O2.
Gas.
Gaseous.
Is it balanced?
No.
No.
Okay. What do I need to do to balance it?
Oh, you're three.
First, we identify the elements and then we count.
You can add a 2 in front of the NaNO3, and then you can add a 2 in front of the oxygen on the product side, I
Okay.
think. So it would equal 6.
So you're saying 2 here?
Yeah.
2 here?
Yeah.
Okay.
Or, yeah.
So then that would be
That's
2,
fine,
2.
right? No,
Let's see.
wait, hold on.
O's.
6,
So
4.
that's 6 O's. That's 4 plus 2. That's 6.
Yeah.
That's 2. And that's 2. Okay. Looks good to me. Okay. So, what else? What else do they tell us here?
They give us a given.
They give us a given. It says, what mass of sodium nitrate will be produced by decomposing 1.50 grams of sodium nitrate? Okay, so what am I going to do with that?
That's our given.
It's going to be our
We'll
given,
start
so we're
with
going to
that.
start off with it. Okay. Then we're going to do what with that?
We need to find the molar mass of sodium nitrate.
Okay, we need to find the molar mass of sodium nitrate. Okay, sodium weighs
23 grams per mole.
okay, and then nitrogen weighs
14.007.
Oxygen.
Okay.
16 times 3.
48.
so oxygen. We have 3 of them. You said 16 times 3.
48.
Okay, 48. Okay, we add it all together.
What do
That
we
would
get?
be 85.007.
So let's just say 85. There's a whole bunch of zeros in that gap, right? And that's grams per mole.
Mm-hmm.
Okay, so how am I going to use that? I just calculated it. What am I going to use it for?
For our second factor, would it be 1 mole of sodium nitrate over 85 grams of sodium nitrate?
1 mole of sodium nitrate over 85 grams of sodium nitrate. Okay, so that's going to cancel that out. So we have moles of sodium nitrate. Are you there?
Yep, we're there. So next
What-
one's mole over mole.
We need moles over moles. Okay, so where am I going to get that mole to mole ratio?
Oh, from the chemical equation?
From our
Yeah.
chemical equation. Okay, and we're looking for, what do we want on top? That's what we're looking for.
2NaNO2.
Okay, so we have 2 moles of NaNO2.
And then 2 moles of NaNO3.
And then 2 moles of NaNO3.
Mhm.
Okay,
Want to put the mole at the bottom on the other side and
moles are going to cancel out. And you said you want to put
Gram.
moles on the bottom.
yeah, and then
Mole
grams on
the
top.
molar mass. of
Okay, so we have to get the
sodium
molar mass
nitrite.
again. So this is the molar mass of sodium nitrite.
Nitrite.
23,
16.
14 plus 2 oxygens. So 2
be
times
32?
16, which is 32.
Add it all up. What do you get?
Let's see.
That would be 69.
That's right, 69. I confirmed it.
Okay, so we get 69. 69 grams per 1 mole, and that's a sodium nitrite.
Do the math now. Let's see here.
That would be 1.22.
Are we done?
No.
No, we're not. I ran out of room. Okay, what is it that we need to do next?
We need
Get the percent yield.
We got to use that yield part. So, okay, so we have 95% yield. So then, if this is what we're going to have ideally, what is it that we actually going to have?
Actually, we have 95%.
So 95% of that. So if I change my 95 to a decimal, multiply it by 1.22. Then that's going to give me my actual.
Okay.
115.9.
You said 115. So 116?
Yes.
Are you sure 116? You're not saying 1.16.
1.16. That's what she meant.
Okay.
Okay, actual over theoretical.
Well, this is our actual. We know that this is our theoretical. So
Yeah, we're done.
we're done. Don't need. There's no need to do extra work. You know.
I know. I'm getting ahead of
Don't need to do
myself.
circles. Okay. Piece of cake.
Oh, yeah.
Now you guys see how to use those chemical equations?
Yeah, unfortunately.
What was, just a quick question, what was the identifier for when it's aqueous?
Solutions.
Okay.
So if it's ever in a solution, it's aqueous. Also, if they don't say anything about it, it typically means it's aqueous.
Okay.
Unless oxygen, oxygen we know is a gas. Okay,
Yes.
ready to move forward?
Yes.
Yep. Onwards and upwards.
Okay. Okay, limiting reagents. We've talked about limiting reagents before, right? Remember the cheese sandwich?
Yeah.
Yeah? Okay, good. So for those who don't remember the cheese sandwich, okay, so if cheese sandwich is my favorite sandwich, by the way, okay? So when I make a cheese sandwich, we take 2 pieces of bread plus 1 slice of cheese, and we get 1 cheese sandwich.
What about 3 bread, 1 cheese, 2 cheese?
Nah, too much
Too much
bread.
bread. Yeah.
Okay, so if I have 20 slices of cheeses, and I have 10 breads,
Constipation.
how many sandwiches can I make?
5?
That's right, I can make 5 sandwiches. Okay, so what's limiting? Limiting basically means you only have just enough. You don't have excess.
The bread.
Bread.
Okay, so the bread would be limiting. So what is an excess?
The
The
cheese.
cheese, it stands alone.
Okay. You guys get the concept?
Yeah.
Yes.
Yeah.
Okay, so this works in chemistry just the same way, right? So like, at home when you run out of cereal or you run out of milk and you only have cereal, right? You can't have milk for your cereal, right? You can't have cereal and milk, right? So because it's limited. Okay, let's take this in consideration for a chemical reaction. Okay, so here I have 3 carbons. Here I have 2 oxygen gases, right? So, and we're making carbon dioxide. What is going to be limiting? What is going to be excess?
Would it be the excess carbon?
Okay, carbon is going to be excess. Why?
Because we only need 1 to make CO2. Carbon dioxide.
We only need 1. So is that the reason why it's in excess? So if I have 2 molecules of oxygen and I have 3 molecules of carbon, and there's a 1-to-1 ratio, I need for every 1 carbon, I need 1 O2 molecule to make carbon dioxide. That's what the chemical equation says, right? Is that
Right.
true? Okay. So why is carbon in excess?
There's 1 more of it.
Because we have 1 more, right? We have 1 extra. We don't have that oxygen to match up with, right?
Oh yeah, it's right there in the picture. Hello. Just realized that.
So as a result of that, we're able to get 2 molecules of
Yeah.
carbon dioxide, right? And then we have 1 unreacted carbon because there's no oxygen to react with. You get it?
Got it.
Good. Anyone else get it? I know Heather got it.
Get it.
Anybody not get it? Perfect. Okay, so things that we want to do when we're working with limiting reagents. The very first thing that we always want to do is we want to sit there, if we have grams, we want to convert those grams into moles, right? Then we want to convert like both sets into moles. And then we want to compare, I like to say compare apples to apples. So we want to change the unit. So we want to use that molar mass ratio to figure out how much. If I have one, how much will I need to make the other, right? Or how much of the other will I need to react complete, okay? I'll show you what I'm talking about here in a minute, okay? And then you want to sit there and compare that number to the number that you actually have, okay? So let me show what I mean. Okay, let's see. There it is. Oh, sorry. It's been a long day. Okay, so I'll read the question. Calculate the mass of antimony 3 iodide SBI3 that can be produced by the reaction of 129 grams of antimony and 381 grams of iodine. Also, find the mass in grams of the elements that will be left. Okay, so what are we going to do first?
We need to find the chemical equation.
We need to find the chemical equation. Okay, Alex, are you there? So what are my two reactants, Alex? No, Alex? Daisy. Daisy J, not Daisy O. Are you there?
Anthony.
Anthony, okay. So
Yeah.
we know that antimony is SB. Okay, and? What is our other reactant?
Iodine.
Iodine. So what is the chemical formula for iodine?
I2.
I2. And we're going to make Diana, what are we going to make?
Which Diana?
The one that just answered.
Right. We're making SB I3.
Okay. Okay, so this is balanced.
No.
No. What do I need to do to balance it?
Can we add a 2
Add a 2 where?
in front of the SBI3 and the product side?
Okay.
And then we can add a 3 in front of I2 on the reactant side,
Okay.
a 3, and then a 2 in front of SB.
Okay. So is that balanced?
It is.
Yes.
Yeah.
Okay. Okay, so now we have a balanced equation. What's next? Okay, Michael, what's next? The givens. Oh, we got a couple of givens. So they give us 129 grams of antimony. Let's go ahead and start with that guy. So if I go 129 grams of antimony, so what do I need to do with this?
Do we find the molar mass?
We're going to find the molar mass. So what is the molar mass of antimony?
121.76.
So it's 121.76
Yes.
over 1 mole. Okay, so that would be how many moles of antimony?
Zero six.
Would it be 1.06?
Okay, 1.06. Okay, so then that gives me the moles of antimony. What about iodine? So we also have a value for iodine. And this is always a hint. If you have both of your reactants, they give you masses for, that probably means that the problem is a limiting reagent problem. Okay. So we're going to start off with that again. So what is we said the chemical formula for iodine is I2. Oops, sorry. Grams of I2.
So it's going to be 126.9 times
Okay.
2.
Times 2, right?
Yep.
So 126.9 times 2.
That's 253.8.
253.8.
Yes.
And that's grams per 1 mole. Of I2.
$1.5.
Okay, 1.50 moles. I2. Okay, so both of these are what we actually have. So I'm going to write half. So we have this much. Okay, so if we use up all of the antimony, can we figure out how much of iodine we'll actually need? And how will we go about doing that?
Oh, we will the coefficients in the chemical equation.
So we need that mole to mole ratio. So we're going to use our chemical equation. Okay, so we're looking at antimony to iodine. So it's ratio is what?
2 antimony
2 moles of antimony. Okay, at the bottom.
per 3 of iodine.
3 moles of iodine. Okay, so this will give us our moles that we would need or what we want.
Would that be 1.59
Yeah.
moles of iodine?
Okay, so this again is our need. So for us to completely react with all of this antimony, we're going to need 1.59 moles of iodine. What do we actually have?
1.5.
Okay, so that tells us what? What will that tell us? What's limiting?
The iodine.
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 Okay, so we know that the iodine is limiting. Okay, so we can only make as much of the as much antimony 3 iodine that we have iodide. Okay, so that means that we're going to want to use this guy to sit there and calculate how much of our product we're actually going to make. So we're going to take those moles. We have 1.50 moles of I, 2. So how can I calculate the number of moles of SBI3 I can make?
Would it
The
be
2 moles of SB over the 3 moles of iodine.
Okay. Give me SBI3 over 3 moles of iodide. Okay, so our moles of iodine is going to cancel out. So we get one mole of SBI3. So how can I change this to grams?
You need to calculate the molar mass.
I need to calculate the molar mass. So molar mass of SBI3. We know that SB weighs 121.76. And then we know that I3 is 126.9 times 3.
Would it be 502.46?
Altogether?
Yes.
So you said 500.
2.46.
Okay. Okay, 502.46. So grams per mole. Thank you. So 502.46 grams of SB
Per mole.
I3 over 1 mole of SBI3.
That would be 502.46.
Yeah, the worst part was I was going to plug into my calculator.
Grams of SBI3.
Okay. So that's part of the question, right? The other part of the question says also find the mass in grams of the element that would be left. There's 2 ways to sit there and do it, right? One way is we know by the definition of what you put into a reaction, you got to get out of reaction, right? Conservation of mass, conservation of matter, right? So altogether, we're putting in a total mass of, we have 129 plus 381 grams So we're getting 510, but if we subtract this guy, 502.46. Okay.
7.54.
So we'd have 7.54 grams left over, right? And that would just be of our SB. Okay, so that's one way of calculating it. The other way of calculating it is actually going back and figuring out how much SB we actually used, then subtract that. So we would do that by using this number here. So we have 1.50 moles. Let me put it in a different color. Moles of iodide. The mole ratio, it's 3 moles of iodide to 2 moles of SB. I believe that gives me 1. Okay, so we're actually only going to use up 1 mole of SB. So we have 1.6. So if we have 1.6 minus 1 mole, and that's going to equal 0.06 moles left over of SB. And if we multiply that by how much SB weighs, which is 121.76, we should get close to what we got.
That's 7.31.
Okay, not too bad. 7.31, 7.54. It's all dependent on our rounding there. So, okay. Questions, concerns, Cash?
What does the Z equals 51 mean in the question?
What is the atomic number of SB?
Oh, okay.
51, right? It's giving you a hint. Because a lot of people have trouble finding what SB is on the periodic table. Okay.
Okay.
Okay. So there are a couple of ways of getting to the problem. In the notes that you're able to download, there is another way that you could go about doing it. The other way of going about doing it is calculating for both cases, just calculating the SBI in both situations. And the one that gives you the lowest value, that's going to be your answer. Here. But I like this way. It's not as much work. Okay. Let's see. Here. Okay, so this is just showing you the other way of going about it. Okay, so energy. So at this point, you guys know a little bit about energy. You know that if you have to put, well, I should say heat. We've talked more about heat than energy. Okay, so the units for energy, it's joules. That's the most commonly used unit. That's one of them. Now, a joule is just basically, it's the force of 1 Newton applied the distance over a meter. Okay? This is the SI units for energy. So again, 1 joule equals, in this case, it's going to be 1 kilogram per meter squared second squared. Okay. A calorie, small c calorie. So that's going to be the energy required to raise the temperature 1 degree for a gram of water, or 1 gram of water, 1 degree. Sorry. Okay. So 1 calorie is going to equal, or 1 small c calorie is going to equal approximately 4.184 joules. Okay, so we know that that's going to be a nice little conversion factor. A kilojoule. So we know a kilojoule is going to be 1,000 joules, right? And then we know a kilocalorie, kcal, that's going to be 1,000 calories. Okay, so then 1 kilocal is going to be equal to 4.184 kilojoules. Now, a food calorie is going to be, that's a capital C calorie. That's going to be equal to 1 kilojoule. I mean, 1 kilocalorie. So 1 capital C calorie equals 1,000 small c calorie. Okay, are you with me?
Yeah.
That's right, thermochem, exactly. Okay, so let's see those skills. Calculate the number of calories. Calculate the number of kilocalories, calories, and joules in 4.5 kilojoules. And then also calculate the capital C calorie. Okay, so we have 4.25 kilojoules, kJ. How would I do this? Brianna, I haven't seen you text me today. What's going on? You gonna help me out?
One kcal over 4.184.
Okay, so we have
kJ.
1 kcal over 4.184
Yeah.
kJ. That is correct.
Good
So-
job, Christy.
I'm here, I promise. 10.12 or
How many sig figs should we have?
3, so
Yep,
10
10.2.
10.2, yeah.
So the question was, we want to convert to kcals if we're starting out with kilojoules. Okay, Brianna, you ready now? So the question is, if I want to convert 4.250, 42.5 kilojoules into calories, how would I go about doing that?
Someone talking?
Nope. Brianna, are you there? So we can start off with this guy that we have up here, right, Brianna? We can kind of adopt that one. And we know what is the relationship between kilocalories and calories. How many calories are in a kilocalorie? How many small c calories are in a kilocalorie? Veronica.
She's in
Oh,
the
there we
chat.
go, 1,000. I see it.
Trying to figure it out.
So for 1 kilocalorie, she says it's 1,000 calories. Okay, so then kilocalories are going to cancel out. KJ is going to cancel out. And we're going to end up with 10,000 calories. Okay. What about capital C calories? We know that capital C, 1 capital C calorie is going to equal 1,000 calories. So then we can kind of use this equation here, or we know that the capital C calorie is just going to equal 1 kilocalorie. So then we could just say 1 kilocalorie equals 1 capital C calorie oops. Okay. Wilmer, you've been real quiet. How many joules do we have? If we have 42.5 kilojoules.
42,000.
We have 42,000. So we know that a joule equals, 1,000 joules equals 1 kilojoule. 2.5 thousand. Okay. Questions, concerns, Cash? Credit? Good. Okay, so thermal chemistry. So when we start talking about thermochemical equation, we're going to be looking at what we call the heat of the reaction. This is called the enthalpy of the reaction, or we call it the delta H. So often you'll see it written as just delta H or delta RH or delta R reaction H. So you'll see it a couple of ways in science. So if a system is endothermic, you guys remember what endothermic and exothermic means?
One releases, one absorbs.
That's right. One releases and one absorbs. Good job.
Yep. It's my topic for the parody.
Oh, see, you learned something, huh? Okay. So when we talk about endothermic, right, an endothermic reaction, I like to look at it as we're putting something into the reaction. Okay. So you're going to be putting into the reaction. So that's going to be on the reactant side. Okay. Exothermic means something is going to be released. Okay, so then that means that that guy is going to be on the product side. Okay, now I'm going to show you what I mean by that, right? So endothermic means that the reaction is absorbing energy. It needs energy to kind of keep going. Exothermic means that it releases energy. Okay, you guys got it?
Yeah.
Got it.
Okay, exothermic is going to be a negative value for delta H, and endothermic is going to be a positive value for delta H. Again, the way I like to look at it is, if I'm putting it into the reaction, it's positive, it's going in the reaction. If it's being released from the reaction, it's negative, being let go. Okay, so when 2 moles of ethane is burned, 2,855 kilojoules of heat is given off. Okay, this reaction is an exothermic reaction. Okay, so we set up our equation. There's 2 moles of ethane, so we balance the chemical equation, and this is considered to be part of the chemical equation. So there's 2 ways of doing it. We could write the equation in this fashion, or we have it written as a side statement. Since it's an exothermic reaction, we know that it's going to be a negative value for the 2,855. If it was an endothermic reaction, it would be a positive value. Okay. Or we could write it this way, where we actually put it as part of the chemical equation. And this, in this case, it really should be per mole, right? When we talk about enthalpy, it technically should be per mole. But in this situation, right, we're saying that we're starting out, we're basing it upon this equation. So for every 2 moles of this guy, right, that's how much energy we're going to get. You guys with me so far?
Yes.
Okay. So here's an example of an endothermic reaction. So this is the decomposition of ammonia into its elements. Okay, so 2 ammonia, and in this case, we have a positive value for the enthalpy. So that means it's going to be on the reactant side of the reaction. And that's going to yield nitrogen gas and hydrogen gas. Or we could write it like this, where we have the 2 ammonia gas yields the nitrogen gas and 3 hydrogen gases. And we write it as like a side piece. Okay. So those are the 2 ways of writing it. Okay. Comfortable? Good. Since nobody said anything, I'm assuming you are. Okay, Joanna, are you ready to test it out? Are you there, Miss Diaz? That's all right. Tucker's going to help me out. Are you there, Tucker?
Yes, kind of.
Okay. So I'll read the equation. I will read the question, and you help me write the equation. It says the thermal decomposition of limestone, solid calcium carbonate, CaCO3, S, to lime, solid CaO, S, and gaseous carbon dioxide, CO2, G, is an endothermic reaction requiring 178 kilojoules per mole of calcium carbonate decomposed. Okay, so how would I write the chemical equation or the thermochemical equation in both forms? First thing I'm going to do is what?
Write the chemical equation.
Okay, so let's write the chemical equation. So what is my reactant?
Is it CaCO3?
CaCO3.
Yeah.
We know that's a solid. Okay,
Is it plus CaO?
Oh, yes.
is it gonna be plus or
No.
is that?
No, it's not. It's
We're gonna go the yield
yeah,
sign.
Oh,
yeah, so, yeah.
Okay,
Remember CaO
2.
and then the S. And that is plus the carbon dioxide, which is the CO2 grams or whatever.
okay,
And
okay. Okay. So now that thermal energy, is it gonna be, how are we gonna write that? There are two ways of doing it. Are you there?
Do we have to start with the given 178?
Okay, so where am I gonna put that? You gotta repeat that again. I didn't quite hear it. Is it gonna go on the reactant side or is it gonna go on the product side?
on the
Product?
product side,
Endothermic.
Would it be in the reactant?
Anytime you see endo, you wanna put it, it's going into the reaction. So we're gonna put it on the reactant side. So we put 778 kJ per mole. Okay, that's one way of writing it. So the other way of writing it would be what? Same chemical equation. Come on, it's not that hard. I wish all my questions were like this. Mimic what you just saw. There we go. Delta H equals, so is it a negative or is it a positive?
Negative.
Endo. What was
Would
that?
it be
A negative.
positive?
Positive.
Positive.
It's in the
So
reactant.
endothermic is always going to be positive. Okay, that's it. Easy, huh?
kind of.
Okay, now I'm going to tell you a little secret, right? So we can use this thermal energy just like we use moles, right? So because it's based upon per mole. So if I want to calculate, if I'm given a certain amount of moles, I can calculate how many or how much energy is going to be generated, okay? Okay, so it's going to work in the same process as stoichiometry, right? Here it says, what is the mass of liquid? Liquid in octane, C8H18L, a component of gasoline, must be burnt to provide 9.5 times 10 to the minus, times 10 to the fourth kilojoules of heat. Delta H equals minus 5,471 kilojoules of C8 H18 burn. So in other words, we're going to use this energy to calculate how many moles of this guy we actually have, right? So if we have 9.05, times 10 to the 4th kJ. That's our, oops, working mentally backwards. I know we're over. We need to go to our lab here. Okay. So, and we know that's heat, right? So we can use this value here to calculate our number of moles. This case it would be minus 1 kJ for 1 mole of C8H18. Oops, I guess I should also, what is the, how do I calculate the molar mass of C8H18?
For CH,
So we have 8
maybe
times 12 and 18 times 1. It's 96 plus 18.
114.
Okay. What did you guys get? I got 1,890 grams.
Recording in progress.
What was that? Okay, questions, concerns, Cash?